Okay, so welcome everyone. Thanks a lot for coming out for my talk. It's fun to be at Fosdem. It's my first time here, and I'm excited to talk about this new game engine we've been working on called Redwire. And yeah, I think it's interesting because it's game engine we're trying to do something else. We're trying to do a game engine specifically made for remixing and mashing up games. So we've taken like a really different approach to game engines, a really different approach to the kind of way you can mix games together. And that's what I'm going to talk about today. So I'm going to talk about what kind of games and mashups we're trying to make, about how we have this visual programming environment where that's inspired a lot from electronics hacking, and how you can kind of pull together different parts of a game and mix them together, and the kind of debugging tools and live coding tools that we can integrate into it, and some of the technical challenges involved with doing that, especially in a browser. Okay, so just a few words about where I'm from. So I'm American, but I'm living in Paris and working at this place called the CRI, which is the Center for Interdisciplinary Research. And so it's a lab that's kind of at the crossroads between education, technology, and science. And they do have a bunch of different activities. One of the main activities is education. So there's some higher education programs involving all the way, from masters all the way up to postdoc levels, and also education in schools. And also after-school programs. And the idea, the guiding principle is learning through research and learning through play. And so the idea is that the students, whatever level they are, come with their own ideas and are sort of inspired to learn about science and learn about engineering through kind of exploring the projects that they come up with. Okay. So we also develop our own open source projects there. So one of the projects we developed now is called No Nodes, which is a distributed way to link knowledge across the internet and show graphs about it. This project called Co-Idea, which is it's a platform on the web in order to spark new creative projects among people who don't know each other and come from really different backgrounds. A project called Symbio for All, which is in synthetic biology, in a way to create new projects in synthetic biology. We have some games we're working on. In particular, Irokoli, which Raphael is going to talk about. I think it's 2 more talks. So you get to learn a lot about that and synthetic biology, and some other games around teaching optics and about studying creativity. And we also are working in this domain of citizen science. So if you haven't heard of citizen science before, it's basically like an approach to open science, where you're trying to get both kind of have science that applies to people's everyday lives, and then get them involved in making the science themselves, whether that's gathering data for a scientist, or actually doing analysis, or even coming up with their own ideas for the kind of science that they would like to do, and learning about science as they're carrying out their own experiments. There's some really famous scientific games that you've probably heard of. One is called Fold It. That's probably the biggest success in the field about folding proteins. But there's many others along those. There's also there's a bunch of gene games also. We actually do sequencing of genes in order to help scientists out when they're trying to understand like extinction and different the way that species are evolving. And as part of this Citizen Cyber Lab project, which is an EU project that we're working on, I came in when I was first hired. This is the project I came in on, and my boss said that we're trying to make games to allow scientists to create new citizen science games. I'm sorry, we're trying to make a platform to create new citizen science games. And so I was thinking about what kind of game engines we might be able to reuse, something like that. And so I had this conversation with my boss, and he was saying, well, we should, ultimately a scientist should just be able to take parts of one game and parts of another game and kind of mix them together, and then kind of add some more stuff like whatever he wants, and then in the end he has his own game that's totally new. So I was like, well, it's that's a really good idea, but it's totally impossible, right? You can't just, I know that you can. I'm a programmer. I've been programming forever. You can't just take code from one thing and mix it to another thing. You could eventually take a library and reuse it or something like that, but you can't just mix things. And he said, well, why? Why can't you? And that got me really thinking, like, it's true that ultimately, we've been programming for a long time, right? All in all, we have lots of technologies out there. We have functions and classes and meta-classes and meta-objects and entity component systems and distributed version control and thousands of technologies and signals and slots and millions of programming languages and billions of game engines and even more libraries that go to those game engines, right? And yet we still can't do this fundamental thing of mixing things together. It's still not easy. And it's true that when you think about it, we all, I think, would like programming to be more like building with Legos, right? You want to move your Lego thing, you just take off the top and you stick something else onto it, right? Changes the color, it doesn't matter. but in fact, when you actually try to alter a system and actually try to mix parts together, that's called refactoring, right? That's like this horrible microsurgery that you have to carry out, where you have to examine every little bit of, oh, hold on a second, but if I take this out, is that going to mess up that other thing? And then you do it, and it breaks everything. And maybe, if you're lucky, you have a good test base, and maybe you can realize exactly, at least, what kind of things are broken. And if you're unlucky, you don't have any tests at all, so you don't know what you're breaking, in fact. And then it just takes even longer. And it's impossible even to know how long it's going to take when you're doing it. And so this is the kind of thing I was thinking about, but I got a lot of inspiration by the inventor of the closure programming language, which his name is Rich Hickey. He has a bunch of excellent talks that you really should, if you're interested in this topic, you really should check them out. It's fantastic. And one of them is called Simple Made Easy, where he basically goes through and he observes in much greater detail than I'm doing now about what things actually prevent you from separating out parts of a system. And he defines this thing called simplicity. And simplicity is an objective measure. It's an absolute measure, where you can say, well, it's about how things interleave. He gives the comparison of kind of braiding threads together. As long as threads are straight and parallel, they don't touch directly. You can easily take one out, you can move it around, you're not going to mess anything up. But as soon as threads are all braided up together in some kind of knot, well then obviously pulling on one, you don't know what's going to happen. And in fact, ultimately that's the problem. It's not so much that it might take you a while, it's that you don't even actually really understand the consequences. When you start building onto a system as you go on, at some point, right, I mean, probably a lot of you have had this experience, suddenly new behavior starts emerging out of your system that you don't understand. Suddenly it just starts doing weird things, stuff that worked before doesn't work anymore. And it's not that you took anything out, it's just that you added new things. And ultimately, why is, I mean, that's actually really cool for games. I mean, we're actually looking for emergence in games, right? We want simple games that you put components together and new things come out. But for programming, it's horrible because, in fact, we have bugs and we can't fix them. And so some of the lessons he came up with, one of the ones I'm really pulling from is, first of all, basically trying to avoid this tangling, try to keep things independent and separate. And the other thing is to leave data alone. So often we kind of wrap data behind interfaces where you have to call a bunch of methods or functions in order to access the data and modify it. And that also is a barrier to putting things together because you need a new API if you want to use a different system. Basically a saner abstractions around time and memory. Basically the idea that in a lot of systems, memory might just change as you're working on it. You're in a function call and you're doing something, and maybe it's multi-threaded and another thread comes in and changes what your memory you're working on right now. Or maybe it's an asynchronous event, like in JavaScript there's a lot of callbacks. Maybe a callback comes in and changes something while you're working on it. And you can't really plan that out. It's really hard. It's really hard to debug those problems. So another source of inspiration is thinking about how this is done in electronics. Because Legos are actually a little too simplistic, right? A little too basic to actually base something on. Because the interface, okay, these little plastic knobs and stuff, but there's no movement, there's no communication going on. Whereas in electronics, if you take the example of a breadboard, right, where you have rows and rows of pins that are all electrically connected, you can just come and stick a resistor in there, stick a capacitor in there, and they're going to automatically connect, right? Like the interface is just that there's a wire. That's all there is. And it has a bunch of advantages. One is that you can connect anything, so you can just put a new resistor in without changing anything else. You can measure anything anywhere. You can take a multimeter or take a oscilloscope and stick it in maybe several places at once and observe how the system's going on, which also means you can test it, right? Like you can test a subpart of the circuit because you just pull out all the other connections and you can understand exactly what's going on within that part. And you can replace everything. You can take out one thing and stick something else in there. Again, you don't have this problem with the interface. You don't have this problem with recompiling. It's not going to know what the library is, kind of thing. It just doesn't exist. And so try to think about how that might work. Now, there's this thing called visual programming. So I don't know who's used visual programming languages. There's quite a few of them. It's kind of an old idea. It comes from like the early days of computing. There was this idea that, well, you could represent nodes. You could represent mathematical operations as nodes in a graph. And on the top of a graph, you'd have multiple, one or more links coming in, and that's data that flows into that node. And once it reaches the node, well, then it does something. It produces an output, and that flows to the next one down the graph that might take inputs from other places, and so on. And in fact, it's interesting because this actually was not developed as a visual programming language. It was actually originally developed as kind of an alternative architecture against like the von Neumann architecture that eventually dominated, at least all the way up until graphics cards, that nowadays can do things in parallel. The idea was that you could do tons of computation in parallel. And eventually, they kind of lost that argument. But in the end, it kind of resurfaced as a visual programming idea. The idea, well, you can just take blocks and they, do actions and they produce data, and you stick them together like that. So it's very similar to what we're talking about. And there's actually quite a few visual programming languages. Like this is one called FlowHub that's fairly recent, but there's a huge number. Also in scientific computing. And in fact, they already are integrated into a lot of game engines. But the problem is, as you start, these graphs look really simple. They're really easy to understand when it's just a few nodes. But the problem is, when you start adding on to it, you get something like this, right? So this is kind of cool. This is in Unreal. You can actually program a level all using the visual programming language. But no one else can understand it, right? And this is totally crazy. And ultimately, it's spaghetti code all over again. It's just visual this time. So you just realize how crazy it is. But it doesn't help you really understand it. So we tried to think about how we can change that. How can we put some order into this visual craziness? And we had the idea of separating out. Basically, the basic idea is taking the memory out of the blocks. So currently in most systems, each of those blocks might have its own memory, and something that might change at any particular time. And the idea is to take all that out and centralize it into one big memory component. So this memory has a bunch of slots. So these are data slots. They can have whatever kind of data you want in them. And they have pins going in and pins going out. So as you might suspect, you can take, here I'm calling them chips, something that is going to produce a value, going to do a calculation or something like that. It's basically a function. And it also has input pins and it has output pins. And so you just connect them up. So you take out from the memory and hook into the chip. And then you can do it a second time. You can have it go back again. So here we can say that at the result of when this chip does its calculation, it's going to feed back into the memory. And you can have it feed back into multiple places and to a different place. There's no real restriction about it. We can set up a second chip and have it run in parallel to the first. So we can reuse that data again, and again have it flow back somewhere. So I'm just going to take you through how this will be executed. Okay, if you had this kind of setup. So the first thing you do. Oh, right, sorry, one more detail. We can put in also constant values into the chips if if you don't want to store everything in memory, some things you don't need to. So the first thing you do that the game engine is going to do, right, so we're on it's a game engine, so it's on a clock, right? So we're on, say, like a 60 hertz clock. So at every frame, we're going to basically freeze the memory at that point. We don't want the memory to move during the clock frame, right? So we're going to freeze it, and we're going to calculate what the chips are going to get as input. So it's like the chips are pulling in from their pins, right? What's going to happen? And then what's going to happen is all those pins are going to do their calculation in parallel. So they're isolated. They're not directly connected to each other. So if you can take one out and put a different one in, it's not going to change what the first one does. This one at this point is totally independent from that. The only thing they have in common is they're both getting their source data, their input data from the same place. But beyond that, they don't have any other interaction. And then once they've calculated their values, well then, you take that data back, whoop, and you flow it back into the memory. And so memory is now going to be basically reset with new information. Again, all at once. So it's not a thing where one chip is going to write something, and then the other chip comes in real quick and writes right over it, so you never saw the first one. What this is, even if they connect to the same pin, it could detect, if they wrote different values to the same pin, it could detect a conflict. And it would say, stop. You have a problem in your code, right? Which is nice already. And in fact, in some cases, you can even merge the two together. Like imagine the data you're writing is an array, and both chips add things to the array. Well, then it can just make a new array with more stuff in it. It can merge them together in certain cases. Obviously, if one writes 1 and the other one writes 0, there's a problem, and it's better to stop at that point. But you can handle merges in other cases. Oh yeah, please ask me questions also, by the way, as we go, if you have any questions. So I can, yes?
How do you handle scientific differences? If the two chips have as inputs the output of the other, you can just compute them in parallel. So is it an error or?
You can't. Well, the thing is, you can't directly connect this and this. In fact, that's the thing. So they're linked only through the fact that they have a common memory base that they're pulling from, and that prevents this kind of. Because in most visual programming languages, indeed, you hook them up in series. So you have this chip feeds into that chip, feeds into that chip.
Yeah, but if it is a sort of the output of a chip is the input of the other.
Yes, you can do that kind of thing. Yeah, you definitely. But you have to pass through memory each time, which seems like It's kind of annoying. You're like, at first it seems like, well, that's a silly barrier. Why not just hook them up directly? But what's nice about it is, once again, independence. You can take one out, and the first one's still reading from memory. It's not going to fail because it doesn't have any input anymore. Yeah?
But doesn't this limit your performance to your slowest chip?
Well, the idea is they're running in parallel. So yes, if you have chips that did some crazy computation, then it's not a very good way to do it. You'd have to either break up the computation over several cycles, or kind of ship that out to something else that's going to do a long computation and come back with the result. So the idea is that chips only do things that you can calculate quickly within a cycle.
60 hertz.
Yeah, within 60 hertz, yeah. So it has to be pretty fast. Did I see another question? Yes?
So in this case, we have to assume that each computation takes one step, right?
Yeah.
So
right.
if you want to do more than one computation, like a evolution for your game or something, within the same time frame, you cannot. You can only do it like 60 times a second.
Yeah, so it's going to be called 60 times a second. Afterwards, you can, like I was saying before, you can either, if you have something computation is going to take too long, then I guess I'm wondering, is your question that it's taking too long?
Yeah,
or
no,
that
I mean, for example, you have a game and you have AI, and then after the AI, you want to have the player do something, or vice versa.
Oh, okay. So
So
things that don't happen in parallel.
Yeah,
Okay.
exactly.
All right, so I'm going to get to that a little later. I'll explain how we're going to do that. Yes?
Hi. Have you actually studied state machine theory in electronic engineering? Because you pretty much just described the theory of the Moore state machine from
okay.
1963, which
Okay.
is exactly this, that you basically only produce outputs from memory, you centralize the memory, and then you have a feedback loop with a clocked state machine in order to make sure that your logic functions provide the feedback input before the next clock cycle.
It sounds very, very similar, in fact. Yes.
Yeah.
I'll definitely check that out.
Look up state machine theory, especially
Okay.
more state
More
machine.
state machine theory?
It looks, I think you'll probably find a lot of answers to
Oh, great.
issues you're having.
Thank you.
I've seen these kind of things before in electronic engineering, where you see simulation packages for chip design with simulating more state machines, so code probably already exists.
So they're testing the way to build those chips.
I did low-level design and basically simulators for testing.
Okay.
And
Maybe I'll get to talk to you afterwards. I'd like to ask you some more questions about that. Any more questions, or should I keep going? All right, I'll keep going. So, okay, so this we explain basically just writing out to memory. But for a game, that's obviously not enough, right? I mean, memory doesn't do anything. You're not showing anything on the screen. You're not getting any input from the player. It's pretty limiting. So how can you do input and output? And so what's interesting is that we came up with the idea of just having input and output be another kind of memory. A lot like a buffer. A lot like in the old days, I think people used to write out to the screen. You just put a bunch of data somewhere in the buffer for the screen. And then when the screen came around to actually draw it, it would read it all up and draw whatever was written there at that particular time. And so, for example, you might have pins for the mouse, pins for the keyboard, pins for graphics. Right? Obviously, it's a little more detailed than that, but just to give you an example. So how does that work? So we can have a chip, just as we did before. We can hook things up the same way we did before. Basically, we can tie the input and the output from the mouse. Obviously, there's no input here, right? Because you can't control the user's mouse for them. And you can send data back again to some of them, for example, writing graphics. So maybe this chip is drawing graphics on the screen based on the position of the mouse, for example. And you can mix the two. You can have memory involved in there too. So you can have a chip getting data both from input from the user and also the memory, and writing back to both. It can write back to the memory as well. And so just to take you through the same cycle, the first thing that happens when the clock cycle falls, we calculate whatever the chip is. So we're freezing memory in some sense, and we're freezing also the input of the system, right? We're going to say for this entire clock cycle, we're going to imagine that the mouse is at this constant value. So the whole system agrees. We're going to calculate whatever needs to be put into the chip. The chip's going to do its thing and write out both to memory and to I/O at the same time. So I'll just give a little example, a little more practical example. Obviously, it's a little bit of a baby example, but otherwise it's hard to fit things on a slide. So I'm going to do it this way. So imagine we want to both move. So this is a drawing that's going to a diagram that's going to move something on the screen and draw it at the same time. So the first chip. So in memory we have a speed and a position. Okay. We can see that this is sent to a move chip, so that at every cycle, the move chip is going to modify the position and send it back again. And separately, in parallel, we have a draw chip that's going to draw something at a particular position and output that shape that we want to draw. And so when these things run, every time you're going to have the thing move across the screen. And it's done in a parallel well. So once again, the advantages of this is that I can take one out. I can take out the draw thing, and it's not going to affect the movement. I can take out the movement, and it's not going to affect the draw. And I can also just change directly these values. If I don't want it to draw from memory, I can just give it a different value at where I want it to draw. They're totally independent from each other. And to go back to the electronics example, we can also measure everywhere. Right, so we know what the value of memory is at this point because it was frozen. So we can easily go back in time and say, okay, well, hold on. Imagine the thing jumps on the screen and you don't know what's going on. You want to try to understand what the problem is. You could go back to that frame that's not working, and you can say, well, what was the memory at this point? You can look at it. What was the output at that point at each part of the graph? And you can easily go through there and find your bug. Okay, so we've designed a few different kind of basic types of chips. So there's a chip called an emitter chip that basically just calculates values and sends it out. There's a processor chip that has multiple inputs and multiple outputs to do a little more sophisticated things. So it might pull from several places and modify them all at the same time. We have splitters, which take a calculation over a large set of data. It's a little bit like a MapReduce type of operation, or a mapping operation. So if you have a large number, for example, of game objects you want to do the same thing for on the screen, well then you'd have your big list and you'd throw it to a splitter and it would do the same calculation for each one. And finally we have the switch, which is going to get to the question that was asked earlier about how we kind of sequence things together. So I'm going to give an example. So far what I've shown you, you have all these chips that are always running in parallel all the time. So it's not obvious how you sequence your game, right? Obviously, the game has some kind of movement to it. Maybe it starts with an intro screen, and then it plays some music, and then it's a selection thing, and then you're playing the game, and then if they pause, you want it to stop, etc., or then they die. So the way you do that is use this notion of a switch. And so the switch is a chip, just like the other one. So it has input and it has output. But in addition, it also has connections to have children. And what it does to those children, other chips, is that it turns them on and off at every cycle. So what's going to happen now is that at every cycle, when we first start, the switches are going to go through and calculate, based on memory, or based on the user input from the user, which of their child chips should be activated. And it's going to turn one on. For example, imagine it decides to turn this one on and the second two off. Maybe it's just going to do a little sequence, turn one after the other. Now, when we do the rest of the calculation, this chip is going to be active. These ones are off, so they're not doing anything. And at the end of the next cycle, the switch, for example, might have modified the memory, or memory might have changed somehow because of some of the thing. And now the second time, it's going to do it's going to activate the second chip. So maybe this answers your question about how to split up. Does it? I'm not sure.
It depends how you use it, because here, to change from the first chip to the second chip, you still need to run a loop.
Yes, you still run a loop every
And
time.
my question was more like if you need to do multiple iterative operations in the same loop. So you have the player does something, like in this case you have input, whatever, then modify the position of an entity, and then you take that modified position and feed it to the AI because they want to start collision.
Right, so in that case, there's a few ways to do that. One way is to have regroup more logic into the chip, have the chip be kind of big because it's doing lots of calculation. Another way to do it is to I'm not going to talk about it here, but there's a way to kind of farm out a lot of this work to functions. And you basically have functions that do a bunch of stuff for you. And since the arguments, since these are pure functions, a little bit like a functional programming language, you know that given the same input, they always calculate the same output. And so you can reuse that. So once you calculate it once, you can just put in cache what those values are. And the next time it's very fast to do it. So there's another way to do it. Okay. So I don't know who's seen Brett Victor's videos of yes, a lot of people. That's great. That's really cool. It's really cool stuff that he's done. And we were really inspired by especially that video Inventing on Principle, which is one of the really well-known ones, where he shows this great stuff. He shows this thing where he has kind of like it looks like he was taking on stuff off of Braid. And so he has this little, his little character that jumps on a turtle and hops over a big pit. And he says, okay, well now imagine that I decided that it didn't work out for my level, like he jumped too high or he jumped too low, and I want to adjust that parameter, right? Rather than going back and saying, okay, now I'm going to change gravity, recompile the game, play the game again, and try to do exactly the same thing, he just stops the game, puts it on pause. He changes the parameter and he goes back in time, so gravity in this case, he goes back in time and he retraces what happened. And so he can just change this code and re-see, well, what would have happened had my code been different in the past.
We're too full. So, no, sorry. The room is already over capacity. No, it was already too full before. Sorry. It's too full. Guys, please. There's a reason why the sign is up.
So basically what he's doing is going back in time. So what his system's been doing is remembering what the user did at every point. And we can do the same thing. Because once again, we're basically freezing memory and freezing the input and output in every cycle. So we know what keyboard keys were pressed at every cycle. We know where the mouse was, what the network was at that point, everything. And so we can easily go back in time, change the code, and rerun what would have happened. We can also do cool things about muting chips. Like, I talked about earlier, the switches can turn chips on and off. Well, we can do that manually too. We can say, well, I want just this chip active. I want to see what happens if just this one's going on when you're debugging. So it's a lot like in the electronics example, just pulling out everything else temporarily. Except, of course, you don't have to literally pull stuff out because it's a computer. We can find chips. That's another thing that he shows in his video. He shows how he can, well, in his case, it's not a chip. It's a program directly. But he kind of mouses over the screen, and it shows him where in the code, what lines of code are drawing the thing that he's mousing over on the screen. And we can do the same thing, and we can go the other direction. We can say, well, for a given chip, like what is it drawing? What is it changing in memory? All right. Are there any more questions? Afterwards, I'm going to move on to the technical challenges. So. All right. So we're doing this in a browser, okay, and we're letting users write their own code. So obviously, there's a problem because it's all right if you write your own code for your own game, but if you're sharing your game to other people, and you put some malicious code in there that's going to change the web page or do something or have them log into PayPal or whatever, it's a potential problem. So there's, for those of you web developers might know like JS Fiddle and Plunker and sites like that that they already do this kind of thing where you kind of share code snippets across the web. And the way they do it is they have an iframe, that's within the page, and they have it set to be a different domain. And when you do that for web browsers, that kind of sets off the security models of web browsers. And they go, whoa, hold on. If it's from a different domain, I'm not going to let them access the cookies and access the web and different kinds of access the network and these kind of things. And we use a similar thing. We're actually using a kind of a newer technology out of the HTML5 spec that does this. That actually does sandboxing. And you can say, well, I want this iframe to run. And I want it to be able to execute JavaScript, but I don't want it to be able to reach out of its page to access anything else. So that's what we do. So we use this sandbox attribute, and then when that happens, well then we can't call functions directly in that sandbox, so then we have to pass messages back and forth. So basically at every cycle, when the game's running, within this sandbox, it's sending out messages being like, well, this is the memory, this is the input and output at that point. So it's kind of an asynchronous thing, but it works for what we're doing. Okay, and we also have this thing of patching. So I talked a little earlier how in the case that multiple chips are writing out to the same pins in memory or to input and output, we want to be able to kind of merge those things together. Okay, and we've taken an approach very similar to like the way that version control works. So if you're familiar with Git or whatever, when you it's a little bit like you're cloning or you're either forking or you're branching a repository, and two people are working on it simultaneously, and then you want to merge back together again, right? So how does it do it? So typically it creates patches for each one. So the patches is basically just a diff. It's the difference between what the code was before and what the code is now that you've changed it. And so it's going to take whatever the common ancestor was, like the base of whatever your change was. It's going to see what happened in each case. It's going to calculate out those differences, those patches, and then merges them back together again. So that's what we do now. But we run into basically a really naive algorithm, which is what I wrote because I didn't know really what I was doing. Fails pretty quickly once you get to large arrays and stuff. Because in arrays, it's hard to know if you are moving things around, if you moved an element from one place to another, or if you just changed it altogether. Or if you remove a few, it doesn't really understand. So we're actually moving now to using these longest common subsequence algorithms, which are a lot more sophisticated. And another interesting algorithms that we could choose are operational transforms. So that's basically what's used in like Google Docs, for example. I think also in Etherpad and some of those other. And whenever you have like a document online that multiple people are changing at once, it's you doing this. It's like these mathematical operations that said like I changed this thing at this particular point in time, and then they're able to merge together with math and figure out the both deleted characters. That's not the same one, or it is, that kind of thing. Okay, we have this history problem too. So like I said, we want to be able to track the history at all points in the past, well, at least up to a certain limit. But in order to do that, right, we can't write over the memory then, so we have to clone it, we have to copy it, which takes up a lot of space if your memory is big. And so there are better approaches to that. So the one that we're using now is we basically keep, so one way to get around that is which is similar to what Git does, I'm pretty sure. They kind of take a snapshot at some point, like the full version, and then after that they just store patches at each point. So what changed, what changed, what changed, what changed. So if you want to figure out what happened here, well then you go back to the last full copy, you apply all those patches in a row until you get to here, and then you know what the memory was. I mean what the memory was at that point. And of course you have to once in a while store these full ones. Otherwise, when you're accessing ones at the end, well then you have to start all the way at the beginning and calculate it all through, and that takes a long time. And there's actually an even more interesting approach, which is what the closure programming language that I mentioned earlier uses, called persistent data structures. So I wanted to talk about it because I think they're really interesting. So imagine you have a vector or an array, right, of 4 elements. So obviously the more normal way to store that would be have like 4 elements together in memory right next to each other. But if instead you store them as a list, so like a linked list structure where each element points to the next one, you can do some really interesting things. If you have a second list where I changed the first element, I made it into the number 5. But what I can do then is just create just the head of the list, just the number 5, and then have it point to the rest. So now it goes 5, 2, 3, 4. So what's interesting about that is not only can I use this list without allocating memory that I've used for the rest of the elements, but in fact the first one still exists. So I can use both list A and list B in parallel, and they don't run into any conflicts. And so it's a little easy to see how it applies to lists, and what's actually more interesting is that it applies to a lot of other data structures as well. They've done it for trees, for like hash maps, and a lot of other data structures that you may have used. And it's actually pretty fast, surprisingly, which you wouldn't necessarily think. And it's a really nice way to get around cloning data over and over again. Okay. I think this is my last technical challenge I was going to talk about, is this thing of this buffering I/O. So like I was talking about earlier, as we treat I/O like memory that we're writing to. Okay, so it's kind of interesting. It's a little bit of you have to kind of get your head around, you have to turn your head around a little bit to think about things this way, because usually, at least in the JavaScript world, everything is kind of event-based. Like if you want to find out when someone pressed a keyboard key, well, you have a keyboard key down handler, you event, and you have to bind to the handler and to the event, and then you get the event. Oh, they put the keyboard down. Okay. Or similar for the mouse moved. Okay, I got to do something about it. And so what we do is simply transform those over to just memory. So for example, what's the position of the mouse? Well, rather than binding to an event or calling out a mouse get mouse position function, we just have that available already. Mouse.position just gives you the position of the mouse. And similarly for the keyboard, it kind of we have the system keep track of which keyboard keys are down, and it just gives it to you. Now, we're not the only ones to do this. This is also the way it's done in some other game engines. Like I'm pretty sure Unity works this kind of way too, at least for the mouse. Now for output, it's a little more interesting. So for output so typically this would be like in the Canvas API in JavaScript, for those who are familiar with it. Maybe if you want to draw a rectangle on the screen, well, you have sort of a context and you change its style. It's also kind of a state machine. And then you decide, well, fill a rectangle with whatever the current style is. And so this makes a rectangle that starts at 0, 0 and goes to 100, 100. Right? So it's 100 meters square, 100 pixels square. And what we do instead is we just describe a shape object. So this for those who aren't familiar with JSON, this just describes an object, so a set of fields. And we say what the fill style is, the position, the size. We're not even renaming anything. We're not really creating our own API. We're just wrapping the current one that exists. And you just send that out to an list. So when the graphics when the graphics are called at the end of the clock tick, it just goes through the array and draws them all. And we can then separate them out into layers and say, well, only draw. We can separate out and have some drawn in different layers, and even say, well, if a particular layer hasn't been changed, if it's the same, we don't have to redraw it. We can just keep it on the screen, things like that. And for HTML, we can do HTML too, so that's kind of cool, especially when you're working in a web browser. You don't want to have to rewrite like input controls and all that kind of stuff. right, for text and stuff. The Canvas API can do it, but it's pretty ugly. And HTML does it really nice, and you have CSS already and everything you want. So we're using this fantastic library called Rivets.js, where it does this two-way data binding that exists in like AngularJS, if you're familiar with that. It does that kind of thing too. Where basically it has all the elements, and it keeps track of the fact that someone changed the data in a particular text field or checked off a checkbox, and it updates memory somewhere to do that, or it tells you some kind of event. And we do a similar thing. So we have it. We basically use rivets in order to say, okay, well, here's a template, a bunch of HTML I want you to draw on the screen. Here is the bunch of values that I want you to use. So it's going to fill in the text boxes and check off the radio buttons and whatever. And then it alerts us whenever something's changed. And so then we can update it on the next cycle. And for HTTP, so for networking stuff, we just have to get rid of, normally again in JavaScript you do this thing where you send off a request and then you get called back through a callback function asynchronously when the request has completed or failed, whatever happened. And we do basically, again, replace that with data. So we have a data object that describes the request you want to make, and when you get a response, we fill in the response for you. Right. Okay, so not much more to say, except that we're really interested in having some feedback and some help with the project. There's not a lot of us working on it, and we're really excited to have a lot of games. We have a new version coming out in just like a week or two, and I'd be really excited if people want to put their games on it, or give me feedback on their games, or remix games that are on there. We're also going to be running, for those of you who aren't that far from Paris, we're going to be running a game jam based on remixing games, where basically we're going to take a whole lot of we're going to like program a bunch of really basic games like Arkanoid and like Tetris, the kind of thing, kind of clones of those, Pac-Man, and then we're going to just have people during the game jam. They're just going to take those classic games and kind of remix them in crazy ways. So if anyone's interested, I'd be really happy to have you come. And also, of course, if you want to work on the project itself, it's open source and it's online. We're really happy for your help. One last thing I wanted to mention. Is about this. It's this. So we're running this game club in Paris also called the Gamadier. So we have a bunch of invited speakers coming from a lot from the indie game community who come and speak, and we also run these micro game jams, which are basically it's like a game jam but within 3 hours. And so the idea is obviously you're not going to program a thing. It's more like you kind of come up with like a new board game idea or card games, or at least just test the concept with like a paper prototype. And we try to film everything, so we have all these, basically all the interviews are available on the website, as well as some of the results from the game jams. And that's about, oops, sorry. Wanted to show at the very end, so it's going to take a while. Come on. At the very end, I had all the information about how to contact me. If you all right, sorry. Right. So, right, there's the website and Twitter and my own contact information if you're interested. Are there any questions? Yes?
I would like to know in what language is this implemented in. I guess it's JavaScript? Or?
Yeah, well, the games are in JavaScript and most of the engine is in CoffeeScript.
Yeah, because you talked about Clojure quite a lot of time, so why not use ClojureScript?
Why not? Because I didn't know ClojureScript when I started.
Yeah, it's a nice language.
It looks really fantastic, and I think I would have written it in ClojureScript.
Yeah, because lots of things you talked about also is like moving state and everything. They have quite a lot of nice stuff. For example, chorusing, that's asynchronous code in JavaScript, so you can have events like FBP or reactive programming.
Oh,
so you can have events and they get streamed inside your code without having callbacks or anything like that. Like it's similar to Go routines in Go. So you have it's all asynchronous, and also there are propagators, which I don't know if you're aware. They are like cells, and you have data inside cells, and they are connected with the methods or functions, and you can stream data. So it's really similar to what you're doing.
Yeah.
So you could.
Yeah, I probably ended up rewriting a lot of things that
yeah,
we have already.
So it's nice to rewrite. Yeah.
But you're right, though. You're right. You should definitely check it out. Yes.
A lot of game logic is often trigger based,
Mhm.
where instead of observing data, we sort of want to know when it changes. Is it something that ends up being more within the chips, or that you handle with like switches and like externally within the graph?
Yeah, so triggers are really tricky because there's always this problem around like the first time you use something that uses a trigger. Like there's always this thing of like, okay, I'm going to listen to this event, listen to the trigger, but hold on, maybe I need to do it right now as well, right? So that's why at first we didn't really include them directly. Like the idea you kind of just track something continuously, and when you need to do something, you just do it. Like you kind of check the condition at the beginning of the chip. But we definitely something that we thought about adding is something that directly gives you what's changed since the last cycle, which I think would be helpful for some things.
I mean, if you want to have a character jump from platform or like handle collisions at some point, there are stuff that are instantaneous. So
yeah, you're right.
It must
But
show up
I guess the way you end up handling it is you just write out a variable. I mean, in the end, you end up like, for example, with jumping. Like you want them to jump just once, for example, and not jump twice because you still have the space button, for example. Well, you would basically you keep track in memory whether or not you are already jumping, which seems a little redundant at some point. Like you don't have the trigger thing, but at the same time, what it allows you to do is go back in time, change the code, and have it replay exactly what would have happened anyway. Whereas triggers are harder to kind of sequence that way.
So this sort of logic goes inside the chips, or you express this in the graph?
In the graph.
In the graph.
Basically, the game engine handles like passing the data and going back and forth and keeping track of what the state of the game is at a particular point. And in that way, the chips actually are just calculating out values each time. And so you can rerun them over and over again, and they're not going to change the state of the game in any way, which makes it nice to test it, Okay. Yes?
Have you already tried to write Tetris or something and then see what would happen?
Yeah, we've written. I don't know if you remember. There's two games. Well, at the very beginning of the talk, I have a bunch of games that we've been working on, and two of them were actually written on this platform. An older version that isn't as sophisticated as one we have now. So I definitely know it works. We haven't actually written out Tetris yet, but I'm really excited to do that. I think that's going to be particularly fun.
But yeah, I cannot even imagine how it would look like when you merge two games.
Yeah, well, it has a different structure to it. I mean, yeah, I don't have a full example here. It'd be interesting to show you an example. But if you're interested, get in touch with me and we'll try to, I'll keep you updated. And I can send you some examples of full games when we have them. You can check it out. You can see. Yep.
Do you have a visual graph?
So the problem with visual graphs is that like they're really complicated when they get big. They're kind of easy when they get small. So the way we have it is we have basically like just a tree structure. We don't actually show the graph. And then for a particular node, you can click on a node and see where those things are connected. But we're thinking about later on actually making a visual graph. It would be really pretty. It's always challenging how you fit that onto a screen. Like it's really it's hard to like pan horizontally. It's really hard, and to and it's hard to if you zoom out too far, you can't see anything, and if you zoom in, you can't see all other parts. So our idea is more to kind of focus on one chip at a time, and then. But for example, things that we can do fairly easily. Imagine you click on a chip, right? Well, then we know what that chip is connected to, both for input and for output. And then we can so then if you click on one of the other things we can show all those connections. And if you click on one of its connections, well, then you can see where that thing is connected to. So it would allow you to like kind of trace well, what else is modifying this memory? Like what else is, doing output here? That kind of thing. Oh, really? You're going to work? Can you say it again, sorry?
No flow and flow out.
Oh, you've been working on them? Oh, great. Okay. Is it good?
Yeah.
Yeah. Cool. Any other questions? Yeah.
So you mentioned that you can call out to pure functions, and I was wondering how do you ensure that they're pure? Do you have like a special language, or do you just control the API that they can access?
Well, right now we basically clone the data so that they can't do anything wrong. That's the way to do it. But there's probably a better way to do it. I think ultimately, like we're thinking about doing, for example, something that really lacks in JavaScript are like vector operations. So you can't just add vectors together or multiply them or anything like that. And so we're thinking about there's these really excellent JavaScript parsers that run also in JavaScript. And so you can kind of basically decompile the language, change things around, and then send it up again. So we could use that kind of approach, for example, to check that they're not writing out to build memory, or check that they're not modifying something in memory. We could use that kind of approach. I think that would probably be better.
and cloning it each time. There's like, I think Douglas Crawford's ad-safe library uses that. He wrote this JavaScript library back a while ago to make sure that ads aren't messing with your JavaScript. And he uses that kind of approach. It's basically like a sub-language of JavaScript. But it has its own limitations, of course. It's not running at full speed. So, any other questions? All right, well, thanks a lot.